This seat is available. I was able to see it, but
How are you?
I'll stand on the side.
On the floor, guys, come on. It's easier.
It's closer. It's a VIP.
Japanese style.
Yeah, there's room in the floor in the front. This is a very common place to sit for a popular seminar like the one we have today. So if you guys, seriously, if you want to come in and sit around in front of these tables, just on the floor, that's great. All right, I guess it's right about 3:30, so let's get started. Our speaker today is Sangbae Kim. He has his PhD from Stanford. He's been a professor at MIT since 2009, and he recently won the DARPA Young Investigator Award, among other accolades. And I'm really excited to have him here with us. I like to think of a part of his work as redefining machine design in the context of vast, dynamic, legged systems. So it's very exciting. Please help me welcome Sangbae Kim.
Thank you very much for a kind introduction. I've been having a wonderful day visiting many different exciting labs and many people. It's a great honor to give a talk here. Finally, I actually been seeing you only second time. The first time was 2 months ago for a conference, and then finally came here to and give a chance to meet everybody. So I'm very excited, and thanks for coming, all of you. So just for sake of time, I will just go ahead and then talk about my research and what we are doing. So the topic, as you can see, is about learning from biology. So I've been working on bio-inspired robot. It's a very broad, not clear topic, but let me see if I can articulate that. So biology has been a wonderful source of inspiration, especially for an engineer who want to innovate and then create a new paradigm in robotics and systems. And as you can see, many different exciting robots are out there, and then it's developed for many different domains. What I'm wondering, though, is, well, every robot has their own applications and it has futures and all that. But what I'm questioning is how do they even design or get to that point? So as a spectator, wow, that looks like a fly, that looks like a snake, that looks like a dog. Well, that's not really how bio-inspired robot happen, right? I want to make something looks like a cockroach and make it look like a cockroach. That's not really happening. So I'm diving into the deep philosophical side of the design process of how we actually do this. So you have to really, in order to do that, you have to understand how is the biology, how is the mechanical system. So I'm not going to talk about all the biological stuff, but the only thing I want to talk about here is we look at cheetah and then, wow, that must be designed for running really fast. I'm looking every single detail. This probably black dots are good for running. If you think about it, this design solution going through millions of evolution need to evolve to satisfy many different constraints or requirements. And look at it like a physiological constraint. They need to keep their temperature right. They need to reproduce. Well, it would be great if I have a robot that reproduces itself. But that's not exactly what I'm looking for right now. And environment, you know, they have to weather rain and snow, and they need to eat, digestion. You know, how much weight we actually have just for the digestion organ. And then they have an evolution. This is very important. They cannot suddenly have my son will run much faster if my son has a 6 leg. Cannot happen in evolution theory. We can do it. We're playing God in robotics, where we can just design whatever I want to have many different leg, and we can change it like 1 day or 2 days. Their solutions are it's very complex. We don't know what is for what. It's hard to skim out what is important part that I care about. If you look at the robotic side, well, it's another complexity. Our computer is not as good as my brain in some sense. Our actuator is very different from a muscle. I'm going to talk about it today. And application, we are not designing a robot that just set it out to wild and then survive itself. We actually design robots for a certain purpose. So we cannot just copy nature and look at it and then make it exactly like that, and then that might not be even a right direction. Battery is another problem. Manufacturing, we have to cut from the bulk and then put together as animal. They grow embryos, and so there are very many different differences. So in order to really learn effectively, to use in our environment in an engineering purpose, you need to find that common principle, the physical expression that describe the behavior, and then we can learn much more effectively. So that's the core idea, and this is the diagram I've been using. So I'm going to briefly introduce. If you want to make a robot or some mechanical system, you should have some sort of goal. And then with following those objectives, we design it. Can biology play a role? I already introduced the complexity. It's not that simple. You have to go through extracting principle process. That's the most important part of the talk. And usually those principles extracted through by hypothesizing and then doing some process I'm going to show you later. And then you can design it. And then you can experiment and analyzing the system. For example, if you want to make a running robot, you have to look at many different running animals. Why? Because I'm making running robot. Cheetah is not the only animal that runs. Cockroach is running very differently. So you can get gist of running. That is principle running. Maybe this is not the only one, but this is one of them we know. Slim model. And then this abstract representation allow us to recreate, re-embody that philosophical abstract representation into our domain. That turns out to be very different from animal because we go through this principle process. And then we can measure their body center mass trajectory and the ground action force and see if our hypothesis really is valid for that behavior or not. Sometimes true, sometimes not. So you can revisit our hypothesis and the refine hypothesis. And sometimes, actually, this process is so much fun for me, especially because it actually sometimes inspires biologists. So, for example, Baffle introduced in the TED Talk, like, well, we look at how the engineer use a tail in the climbing robot, and they start looking, we haven't looked at it. So they actually start looking at the tail function of the tail in the animal. They start publishing in Nature and all that. So it's actually, there's some mutual inspiration going on. So that's a very interesting point. So as I explained this complexity between these two domains, how to create this filter so you can put through this filter, get the principle out. So this is a process we're developing right now. Not everything is structured because I believe human cannot be replaced by computer. These things, computer will help. Analyzing, I think still human is coming and then understanding, that's interesting, and then find that principle. So hypothesize, and then you simplify it into a certain modeling. You do a lot of experiment with the numerical simulation or robots, and then get all the data, and then look at the data, and then you can get those principles. So we're trying to more and more formalize. We're writing one paper about this, and it's still some part is structured, some part is not. So this is the thing we're talking about. There are many legged robotics, so many people probably are familiar with the slim model, but this is one very good example of what the principle we're seeking for. So spring-loaded inverted pendulum, you can imagine a mass, point mass of spring leg hitting on the ground and then jumping off. That simple dynamical representation, the system represents many different symmetrical running gait, and that helps us a lot in terms of understanding what is really running. Instead of looking at all this complex degree of freedom and then measuring all the detail, we can understand much better way in physically. So I want to show you a couple of examples. This is one of the robots I first worked on. It's called the Ice Pro. We learned from cockroach, and then we study a lot of cockroach, and then we got a lot of several principles. We implemented it, and then at the end, it turns out to be very different. That's why we call this inspiration. There's no mimicry really happening. Sometimes even though you try, it doesn't work. If you want to see in a real speed, this is about 2004. It's pretty old now. It's almost 10-year-old robot. So it does just one thing well, because that's the thing we're trying to understand. When we designed this robot, I didn't look at how cockroach climb. I didn't look at how cockroach eat or how the cockroach, So we only look at running. So we abstract that out. implemented in the hardware, so that's why it only does running. And then Dan Goldman takes this, can I try in the sand? And no, it's not going to work because it doesn't have a feet. And then that's how we actually got motivation. We need to study sand. So it actually became one of the bad example of the bad design of the foot. That actually allows us to design this robot that fast because the legs are so thin. Another example, this might be my favorite examples. I got to work on gecko adhesives. And this is the best example that shows how biology provided new perspective. This completely changed my definition of stickiness. You know, when I think of stickiness is always, oh, there's a sticky material, why it's sticky. But actually that allows change. That no, stickiness is not material property, not necessarily. It's actually the overall effective stiffness that matters. Because gecko hair, this is about 2 centimeter. This is about 5 micron. This is 5 micron. There's hundreds of nanoscale hair. These are same material as your fingernail. These are beta keratin. They are not hydrophobic or neither hydrophilic. They're contact angle 98 or so. This material itself, you can imagine, is like your hair. But somehow, overall, it behaves like very sticky material that stick almost everywhere. There's a lot more going on. It doesn't get dirty, ironically. And it sticks while it's dragging along. That's also counterintuitive. If you think if it's magnetic, yeah, it's fine. But what if it's sticky? You're sliding and it still sticks. Finally, directional adhesion is another thing we found very counterintuitive and very effective for climbing. So that's how we get to the climbing robot working. This is the data from the Keller Autumn. He grabbed CT and the rub against surface and a lot of adhesion. If you do the opposite way, there's almost no adhesion. So that actually was very, very important principle we had to learn from gecko. So this was 2006 now. So this was my major PhD work. So there's a lot of fingers that looks like a gecko. I think that was just more like a mechanical design aspect. But most important thing in StickyBot is actually what are the principles for the climbing. So we talked about that in the paper. I want to just talk about the directionality side. This is a real gecko CT and come out in 45 degree and then curved in. And then the tip of these nanoscale hairs are also aligned in an angle. So our hypothesis was, okay, this angle probably provides this directionality. Because if you drag along, it can conform. If you remove that force, they want to come back, so they detach by itself. So how can you create that principle only? So we create much simpler, much bigger, cruder version of our hair. If you look at real scale, it's actually worse than this. Our hairs are about 1,000 times, 100 times bigger. And this video will show you, this is a real gecko. This is our hair. Real geckos slide and still maintain the adhesion. Ours cannot because ours are too big and attach. The frequency is not fast enough. We have too much hysteresis. But the idea is, again, this is a very good example how we create a similar behavior, abstracting principle, and creating a right effective stiffness to achieve adhesion. This is a very old demonstration video, like show what do you mean by directionality. You don't need to push hard because that's important for climbing. And then once you take out the tangential forces, it comes off. You don't need to peel off, as you can see in the regular carpet tape. It doesn't stick unless you apply pressure. That's why I call pressure-sensitive adhesive. And then you need to apply a lot of force to detach. Our tape doesn't really need and doesn't work in the other way. And then that's all about stress concentration in the mechanical materials mechanics. That's still hypothesis because we couldn't even prove it. Now we try a little more, 7 kilogram aluminum. I was a little careful. You don't need to push hard, but I was scared because if I drop it, it might fall on my feet. But look at this. Our glass is not even moving. You can see the reflections stay perfectly same when I'm taking off. Because the detachment force becomes really zero, even though it's holding. Keller Autumn, the gecko guy, he's studied all that and then excited, can I bring my daughter and hang? He actually asked me, can I be hanged? I said, no, you're too heavy. The glass might shatter. But again, once she's out, this is because the adhesion force is proportional to tangential force. I can just take out with my pinky or I can blow the air, it can come off. So it changed the complete concept of what do you mean by adhesive. This is another small example I just showed you because it's fun. We had a squishy robot project, And then I look at this muscle structure where earthworms squish in the radial direction, and then you can extend the longitudinal direction. There's a longitudinal muscle contract. You can expand radially. So we put together a similar kind of structure, not using this incompressible fluid. We use a mesh, which is used in the cable management. And then we made a SMA-based soft robot. It was fun. And then it demonstrates that we can actually make soft systems. And then just demonstrate that there's no mechanical rigid component that breaks upon impact. Everything is made of fiber except electronics. Some people ask, why are your electronics so strong? And then, well, those are just PCB and silicons. So my student was crushing it, and then it still works, because nothing really, things breaks. Anyway, I think we'll move on, because there's a lot to talk about. The final topic is Cheetah, obviously. So I have the rest of my talk will be all about Cheetah. This video, every time I give it a time, I have to watch it, but it's still excite me. And then gazelle is like a background. And they're similar size animal. They're all mammal. Somehow they're very different. And this video, I think, drew a lot of people's attention. I've been showing about 4 years. This is the only video available in the world. So there's no data we can collect. And then there's a lot of hypotheses thrown into this. Why do they whip the tail when they're changing direction? A lot of people, well, tail's probably helping balancing. I'm not really sure I can call that balancing. That's actually how to fall as fast as possible, how to change as fast as possible. This is another impressive video that cheetah can hunt that just bigger animal and then tumble over and now happy. If you make a robot like that, I probably start from scratch rather. So, if you make a robot, very dynamic robot, you have to really think about many things. You have to make it light and make it powerful and then robust. Daunting task. We started like 2009. I started drawing in SolidWorks, and our goal was the fast galloping and energy efficient locomotion and turning, jumping. Our collaborators are all MIT people, and then I'm going to talk about these three things: structures and high efficient actuator. And then, if I have time, I'm going to talk about how we design a controller. This is picture from last year, slightly different from now, but you can see how similar from the September 2009. And this is a review from the last year. So we start walking and then start running. And we actually, most of the time we spend, last 2 years, we spend most of the time in implementing our controller and real-time hardware. Real-time hardware, I don't have much experience, so that took for a long time. Anyway, so before talking about detailed designs and actuators, I want to introduce energy efficiency, because that's one thing I want to emphasize on this talk. Especially because efficiency in locomotion is not quite the same generic definition of efficiency in machine. Because your machine efficiency usually is defined by how much energy I got, how much work that I did. The ratio is efficiency. In locomotion system, there's no such a thing in rigorous way. That's why we don't call a certain car, this is efficiency 97% of my Corolla is 95% efficiency. We don't call that, right? We call mileage. Because your energy input is always like how much fuel I consume, how much battery I consume. What is my work output? If I draw a system boundary of me, I start here, I walk to my home, and then my potential energy is the same, my kinetic is the same. I didn't do any work. I got a little warmer, maybe. But I didn't do any really work. Maybe I heat up the air like tiny bit. Locomotions are all energy dissipative process. You don't do any work. You're rigorously, if you would say energy efficiency, any locomotive system, unless you climb a hill, your efficiency is 0. So you have to really think about different ways of thinking about it. So for example, if I have a robot actuator, and then this is about 70% actuator. Well, maybe the other way is better. If I have a 50% efficiency actuator, if I double my efficiency is like 100%, am I going to get like twice of energy efficiency? Maybe 30-60 is a better example. 30 to 60, I double the efficiency, my locomotion efficiency double. That's not true. That's completely different, because metrics are defined differently. And think about total power is defined. This is a dimensionalized metric. So total cost transport is the most common metric. Total power consumed, battery power, whatever the fuel power, divided by weight times speed. So weight is coming down, your speed is going forward, you're 90 degrees. So if you dot product, there is 0 all the time. But that's most common and the most practical way to measure it. Going back to the energy dissipated part. So the idea is, okay, in order to travel a certain distance, I dissipate all the energy. There's no positive work. So our target is to minimize all the energy. So we kind of categorize where are the energy loss source are. Battery probably heat up some part, but most energy loss is through the actuator. Any overall muscle, our muscle efficiency, depends how you measure it, is roughly 20%. It's pretty bad, actually. And all the heating coming out whenever you do mechanical work. Mechanical work go through the transmission. Don't underestimate the transmission. Transmission is the biggest problem in robotics, in my opinion. They are pretty bad. Don't underestimate. If you really rigorously measure it, you can get surprising number. And finally, you got into the interacting with the ground. Now we have a slightly different energy loss, which is I call interaction loss. So I call it, why is the reason I interaction? Because they are happening in the boundary of the system. My foot sliding on the ground, friction force times distance, energy loss. Air drag is all happening in the surface area. Impact loss, and then my ground is vibrating, my leg is vibrating. So it's happening at the same time. So I call it slightly differently. So I'm going to talk about how we're going to minimize this energy loss through finding principle. How can I minimize this energy loss? By the way, this is not from biology, right? Because I'm just looking at the mechanical system. And using these principles, I implement in detail part of our robot. So I'm going to talk about most of these. So let's start structure. Let's start from structure. This is the real video. It's not fabricated. We don't know why they're doing it. But the important part is look at the size of their leg. It just scared me as a mechanical designer. And this is too. This is a half-ton animal. I didn't even know that the momentum is this large. And everybody who designed a mechanical system, you should feel a little, that might break right away. And how come they don't break? The previous animal looks like they're experimenting with their leg, but I'm pretty sure they're strong enough. And with that very flimsy-looking leg, are they made out of very special material? They're made out of bones and tendons. Those are about 4 times weaker than aluminum, about 20 times weaker than Kevlar. We have a much better material. Steel, we have a carbon fiber. Somehow we cannot make a robot like this. So I start looking at it, maybe there's some magic in it. So if you imagine a robotic foot and have a lot of force and running on the toe, and then you have to imagine ground direction force times about 3 times if you run hard, and then times momentum, you're going to have a lot of moment bending stress on the foot. So then that's typically how you design a robot. But I look at the human, and it's awfully complex. How can I even think about implanting strain gauge here, strain gauge there, measure it? So okay, let's get rid of all the small stuff, and then this is the things that probably matter most. Their bones are actually multi-segmented bone. You know how many bones are in your hands, and very similar to your feet. They cannot take bending moment because they're not even one piece. And there are a lot of ligaments that are holding these bones together. It's almost like I'm not even sure how to describe. They're like wrapped around the bones. And then their biggest tendon, the ligaments here is the plantar fascia. And if you imagine now, if you apply force, these bones probably taking mostly compression. And then this guy probably taking tensions. How about here? It's almost the same. If you apply force here, this guy will take moment, but the bone can take all the compression, and then tendon take all the tensions. If I draw a very simplified version, you can imagine like this. Typical bending stress diagram, if you apply force. If you wrapped tension material around the leg, you can actually decouple, not all the time, but you can decouple the compression and tension completely. Why is that helpful? Because I can minimize the stress concentration of the surface. So we tested. We designed a robot like that, and then we run FEA, and then we experiment. They match pretty well, and then by adding one Kevlar tendon, I save 5 times of stress because it is a stress concentration. Bending stresses are not usually considered a stress concentration. I start seeing as a stress concentration. You can add 20 grams of material. You can save 5 times of stress. well, this is not really generalized method yet. We just showed the one case. It only works in this configuration. But it gives us insight. Maybe animals are designed to really minimize bending stress on a bone because bones are precious. Another thing we did for structure, we really try to minimize the inertia of the leg because you have to move the leg as quick as possible. That determine your bandwidth of the leg and the speed of the leg. And then that's very well observed in the animal too. If you look at the horses, the muscles are all up there. There's almost no muscle below the body line, and they're all ligaments and tendons that act as spring. So we put 2 motors and 2 gearboxes in one module, and that allows us to have a center of mass inside the circle. So I can bring my leg and then put it sideways. It will stand sideways. That actually really helps and increase the bandwidth. So our leg actually can shake 85 hertz. Mechanical bandwidth is close to 100 hertz. Probably another thing we did to minimize the weight. Weight is always an issue. We create this semi-active spine. So when they are when 2 legs are in phase, they're moving same direction. It activates. When they are not out of phase, there's differential system that actually nullify the transmission. So when you trot, you don't want to use your spine. And then when you start galloping, that start activating. The power is stored transmitted from the hip to the spine. I mean, I'd love to have a separate actuator for that, but that will at least consume for me about 5-6 kilograms, which is substantial for a 30-kilogram robot. So we don't know how it works, but we might be able to show pretty soon. So let's talk about actuator. This is probably my favorite topic. We love to see, our mechanical system can do this. Not just for, fun. We can actually save people, can travel faster, and eventually we might be able to ride. That could be the next transportation. I'll show you. Many people say, well, really? But I'll show you why I'm thinking like that. So I just list about, I was thinking about what kind of actuator do we need? Many people, well, our actuator is not good enough. I want to develop artificial muscle. But what characteristic to begin with do we need to develop this kind of behavior? We need the high force density, high torque density, obviously. And we need high power. So I'm just throwing the whatever I think we need. We probably need impedance control. We all talk about most actuators are very strong and stiff. Our muscles are very compliant. So different expression is important. High bandwidth, artificial actuator, our electromagnetic motors those are much faster than muscle. But it's still good to have a higher bandwidth, so we can take advantage of that controllability. And obviously, we need the efficiency. It would be great if we can create those in soft structures so we can protect our body. Our muscles are not only just activating when you fall, protects our bones, and also allow us to design much more flexible way. So I started studying motors 4 years ago. So what is really limitation? So I started looking at literature and then how powerful the muscles are. Numbers are varying so much because everybody testing different way. And then the best number I saw was 300 watts per kilogram, which was kind of extreme, kind of outlier. Most numbers I saw was like 80 watts per kilogram, 100 watts per kilogram. We don't even know that's physiologically sustainable number. And then I started looking at motor power, and then look at maximum motor chart and all those famous motor company. It's about 300 watts per kilogram or a little less. And then I found this other motor companies running high speed. For example, thin gap motor, they start making new ones, and they say 11 kilowatt per kilogram. Tesla motors, they're saying that, well, their motor can be easily 7 kilowatt per kilogram. I look at helicopter motors, they easily achieve 2-3 kilowatt per kilogram. What's going on here? Like 2 order magnitude difference between electromagnetic actuator and then our magic dream human muscle. Why can we make our robot jump up and down 10 meters up and high and then run 10 times faster than me and flying or swimming, whatever? Like we can exceed animal at least order magnitude better than right now. Anybody has any idea why we cannot even though we have such a high power actuator, we cannot achieve those. Our control is bad. That many people say that. I agree. We are working on it. It's not that simple question. It's actually it's just tricky. One simple answer I can give you: these powers are available in only high speed and very low torque. And our muscles are opposite. If you imagine momentum, if I crouch like this, my quadricep handles, I remember, about 10 times my body weight, just holding it, not even jumping or running. So momentum is very small. Why do we have momentum small? Because so I can have a large moment, large range of motion. If I have a large momentum, my arm probably got stuck somewhere here. Our muscles are very different. Our muscles are much high force, not so much power. So then why don't we just use a gear reduction system? That's where all the problem happen. That's where all the problem, control problem, design problem, transmission is the biggest problem. So bottom line question is, how can we achieve high power in low torque, low speed range, and high torque? And then now I start looking at what is really torque limit. This is I actually use the same color. If you look at the Maxon catalog, Maxon is a great company, by the way. I'm just saying that we misinterpret their spec sheet. This is continuous torque, and then this is their voltage. This motor is a 12 voltage motor. This motor is a 36 voltage motor. Draw a line. Everybody learned this torque speed curve for motor, and don't go outside this box. Outside is dangerous. There's out there. Don't go outside. Why? If you think about this blue area is actually continuous power. There's nothing really fundamentally physically stopping going this direction. Well, there's other things like commutation speed is problem. There's a magnetic hysteresis in the steel. Well, how about ironless motor? Okay, so that doesn't really matter. You can keep on going. If you use a magnetic bearing and then put in the vacuum and then very high power speed electronics, this one, I don't know when it's going to stop. If somebody came in, what is the maximum power of this motor? I cannot answer that. Company answer that because they don't want us to go crazy in the burn motor and complain. And this is continuous torque. Imagine when I'm running, what is torque profile is going to look like? Going to be my quadricep, for example. It's never going to be continuous. It's going to go shoot pretty high. Why not going up? Why not going up? Nobody says it's going to be dangerous. It's going to burn if you keep on doing it. But it completely depends on thermodynamics, right? So how much you can go up? So I found this demagnetization torque. If you put too much current, your magnetic field is too strong, you start demagnetizing your permanent magnet in permanent magnet case. If you have induction motor, maybe you don't even have that. Well, they will saturate the metal first. So that's why I found, how about saturation torque? That doesn't really limit, but after saturation torque, your current is kind of like useless. So it's just burning heat and not much increment torque. So okay, so that maybe is the one that I can think as a limit of the motor. No motor company set this in their spec sheet. Many motor companies says peak torque or store torque. That's not this. Most company are not. Maybe a few company does it, but most company this is not accurate. Our motors are not. It's about twice difference. So now you have a much bigger space you can deal with instantaneously. This is about 10 times usually. This is about 3 times, 4 times. Completely depends on design. So you have to actually figure it out by yourself, experimenting. So these numbers, our motor, this motor is 100 watt motor, 200 watt. That's useless anymore. It's not an important thing anymore. How can we achieve a higher current? This is a constant voltage. Why don't you increase the voltage? Maxon told me use 24 voltage. You don't need to stick with the 24 voltage. The Ice Pro running robot cockroach robot that I built in 2004, there was a 6 voltage motor from Maxon company. I use a 32 voltage. It runs 1 year, no problem. It's all about heat, right? As long as your torque is under continuous torque, it's okay. You can keep on using it. If your RMS, if you're going up and down, if RMS is under continuous torque, you're fine. If you have a thermal motor, if you have thermal temperature, you can use your motor 10 times stronger than what you have. So how do you achieve high power and high torque range? I started looking at all kinds of the motor size and looking at it, and I found this most important metric. I think many people actually knows, even some motor book tells you about this. So if you follow me, if you design a motor, something like this, and then keep a couple of dimensions, keep this thickness, there's magnetic thickness, and then stator thickness. And so if you cut out a section, the magnetic characteristic should be same, even though I increase the diameter or increase the length. You're just area change. If you keep that as an assumption, it's a little aggressive assumption, but if your diameters are big enough, that's not too far apart. So I keep all this thickness the same, and then one option is a lower diameter and a longer length. And the other one is, instead of increasing length, I increase the radius, have a same mass. Can you follow that? So this is kind of weird scaling. Your mass is same. And this will be about twice stronger than, it depends on the length. If this diameter is twice as big as this will be about twice higher torque. So now I want to compensate with the gearbox. So I want to have a gearbox to match up with this guy. And then ignore gear friction, ignore gear mass, gear inertia. And I calculate what I calculate. I calculate torque density, the torque. This is not really. So let me just follow. So torque divided by mass is torque density. I want the maximum torque per mass, right? It's the same if you follow that. And another metric I want to emphasize, I want to have a high bandwidth. So how about torque divided by inertia, rotation inertia? They are the same. But I said I ignore gear friction and gear mass in the gear inertia, right? If I start adding this, you always win going this direction and going this direction. And then you could probably find most robotics lab motors are looking like this. Because there are many reasons, the manufacturing reasons and cost issues and frames easy. But in terms of the torque density, in terms of the one that we want, this is always the winning direction. So if you ignore gear mass inertia, torque density, torque inertia, and bandwidth are actually same either way if you ignore gear friction. So we propose a new paradigm. I'm not even sure if I can still call new because haptic devices are designed this way. So this is typical manufacturing robot. They want it to be as stiff as possible. If you want to do some force control, I need to have a force sensor. But those has to be even stiffer to get the right torque. And now what's the problem? If you have an impact, like a cheetah running, right? Your impact force travel, some people might get confused what I mean by force travel. The wave travel, the molecular force in between, any force, you have to think about those molecules that are hitting, pushing each other. That force travels at the speed of sound, and if it's steel, yes. If it's aluminum, speed of sound in aluminum. How fast it can travel? It's very, very fast. No matter how fast you close the loop, and even though you close the loop in time, your motor cannot even respond because your motor bandwidth is so low. So you cannot handle impact in theory here, even though you ignore gear frictions. So people start using series elastic. It's popular. If you go to a robotics conference, everybody's using it because it can handle impact. And now you can measure force by measuring this deflection. It's a great idea. You can make efficiency higher. I'm a little bit hesitant about this complexity of gearbox, efficiency of gearbox, and then I need to change the stiffness also. So we propose if you design a motor, choose to design a motor properly, and then minimize the gear ratio, minimize the gear inertia, gear friction, I can actually achieve everything. If I have an impact, of course, to impact travel at the speed of a sound, there's nothing holding on it. There's very little inertia and the friction going on. So I will show you what I mean by that. That's when our Cheetah is turned off. That's a minimum inertia. So I don't mind hitting it, hammering it. There's travel, there's shock, but there's so little because there's nothing backing on it. So now you can do something much more dynamic behavior without requiring even spring or force sensor. And you can make robot behave like as if I'm doing some force control. This is just position control. Many people learn the control kind of like a different way. So learn position control, force control different. This is just position control. I'm just commanding PD and joint space, and then you can achieve any compliant behavior because our inertia is very low to begin with. This is all true from haptic device. Actually, it's done 20 years ago. Somehow never transmitted to real high-power robotic systems. We create this video just to translate this idea. This is how you're supposed to build a robot if you want to do dynamic system, dynamic application. So we set the radial stiffness, We cannot do research without hammer. We have to have a hammer. There's no stiffness and the high damping. This is, I can change in 1 millisecond. So it depends on how fast I'm closing the loop. 4 kilohertz is no problem. And I can create whatever nonlinear or step or deadband is programmable impedance to begin with, right? And then I can combine it into a shock absorber. Our legs are a little too compliant. We're trying to make it stiffer so that it doesn't have an internal vibration. And then we can crank it up to all the way to a level that it becomes like a sculpture, become a rock. Now we can actually achieve about, without going unstable, twice of this and then 4 times of this. So now it become like a plastic is bending. And that was a commercial motor, and then that doesn't satisfy our peak torque need. Jeff Lang is professor in EE department collaborating with us. He designed a new motor which exceed quite a bit from existing technology. Weight is 30% lighter, motor constants about almost twice. This is a torque divided by I square. How much heat I need to generate that torque is much better. Maximum torque is about 3 times because there's a multiple design aspects optimized. So our Cheetah, new Cheetah is designed that way, and we're excited about it. Another advantage of having low impedance, you can actually regenerate power, which is actually very obvious if you think about any electric cars. And in this particular case, we drop the leg, and then we measure how much power going this direction, that direction. And measuring is pretty accurate. One is measured from battery, and one is from all the drivers. And then match pretty well. Our about 53% of energy is recovered. The rest is burned through the I square R. It's not as good as spring, but the thing is we have all the controllability. So damping, the worst damping is actually already means dissipating. But in our case, that's not really true. We have a lot of damping and hit and then do negative work. Actually, quite a number of percentages go to the battery. It depends on, so we don't know what words should I use. Damping sounds like it's dissipating, but actually it's not in this case. So this is our last May. We've been kind of delayed. We love to try a new gate and new robot. You can see the Cheetah 2 over there. It's not yet so impressive running, but this is limited by treadmill. This is a 2,000 treadmill from Solo. We cut in half and then make it longer, buy longer belt, and then motor's not powerful enough. So we tried to change the gate from the trot to gallop, and then controller wasn't even ready. It was just tried for our curiosity. So you can see a little better in slow motion, and then you see the phase are shifting, and then becoming like gallop. It looks great in first steps, and we don't do any pitch measurement or even changing the trajectory. You should at least change the front leg and rear leg differently. The function front leg and rear leg is quite different in this particular gate. Anyway, so we couldn't achieve the maximum. We couldn't try what is the maximum speed, but it gave us quite a bit of important information. Peak power of the 8 motor, all 8 motor, electric power was only 3 kilowatts. Wow, 3 kilowatts is a lot. If you divide it by 8, it's not that much. Average power is only 900 watts. If you divide it by 8, each motor is only consuming a little bit over 100. Still, surprisingly, Joule heating is 76%. And probably not true in many other robots, but probably compensated by the transmission loss. And the mechanical power is pretty low, but the cost of transport is actually pretty good. And with the 3 kilogram batteries about this big, we have a dummy mass on the robot. You can run about 10 kilometer or 6 miles. With the new motor, if I replace motor, the drop like much more significantly. We can double the distance. So if you think about Joule heating divided by 8, each motor is only burning on 100 watt. So it can run several minutes. If you drop the speed about 4 meters per second, it actually ran. We tried to run about 20 minutes because there's department want to take a video. So okay, keep on running. We break some bearings, but the motor was fine. So this is actually very interesting data.
Sorry, 0.27, is that correct?
This is estimated. This is estimated, yeah. Because we know what, if you run exactly the same way, I know the torque constant, so I can estimate. So we're trying to get this, yeah. So this is interesting data. So cost of transport is a function of speed. In the beginning, it's probably like walking awkward, so it's not very good. 1 is not too terrible, but it's not good. But there's a significant drop. The gradient is pretty steep here. That's actually a very interesting part. And then that kind of corresponds to these bumps. What do you mean by this bump? This is power to speed. How come power reduced as speed goes up? And this is where about fruit number is 1. What do you mean by fruit number 1 is your centrifugal force. If my leg is a strut, and if this center mass is a point mass, you can imagine like throwing something on the ground, and at this speed, your centrifugal force is the same as your gravitational force. You can stay in contact. You cannot walk in the speed. So that's where most animals or people transition to gait and running. So most animals running either lower than 1 or higher than 1. They don't like to be around 1 because it's very hard. And then that seems like it's matching really well with our number 2, this speed, and that's where the fruit number 1. After that, it got better. And then after that, cost of transport drops a lot. More interesting thing is they actually never got back up. It's still going down. And if you compare with the horse is about, I don't know, at least 1.5 times heavier than bigger than our cheetah. Weight is, I don't know, like 100 times, 10 times bigger. They actually already gallop here. And well, of course, there's many differences. But animal, much bigger system, already want to gallop and doesn't want to trot. How come our robot is fine and cost of transport is still going down? Of course, we don't know exactly why they change gait. We think it's energy efficiency. But if that is efficiency is a reason, our cheetah is actually still going down. Our minimum the best speed for trot is maybe is higher than 6 meters per second, which is very odd to think about. But if you think about the difference between muscles and motors, that just might be just naive question. That might be just very obvious. I can tell you, for example, muscles are very picky. If our muscles are stretched, your force is very low, getting stronger, 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 and then getting weaker, 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 weaker. So your force is dependent on the position. And then if I move fast, your force drops significantly. So you have this constraint. Imagine you're running back and forth. You need to swing the arm, swing the leg back and forth. This is the time you need to get the maximum acceleration. That's the time these muscles are stretched. You cannot generate high force. How about electric motors? If I have enough battery, we use a 100-volt battery. Our torque is independent from position because rotary motor, and independent from voltage, independent from velocity. In whatever the velocity, as far as the voltage allows, I can generate maximum peak torque, 30 Newton meter, for the new one, 10 Newton meter. So robot doesn't really care moving fast, back and forth. That's why you see like a unnatural behavior where our efficiency is still very good. So you have to really understand what's the core technologies are different in animal and robot, and then we can refine what can do even better than animal. So how much we can do better than animal? So this is log minimum cost of transport, the efficiency metric for the locomotion. This is log mass. This is from the very old literature, and it's still very inspiring. This is running animals. It's all here. And then this is flying animals here. And swimmers. Swimmers are surprisingly the most efficient locomotive mode. We probably need to understand more. Probably the gravity is an issue. They don't need to be under gravity. So human is pretty good. Human is actually, we think it's human because human leg lengths are relatively longer than other animal per weight. Shimo, I don't know what's the number right now, but this is a number from old days. It's still pretty bad. It's a log scale. And hydraulic robots are way up here because they're burning all this fluid. And then real cheetah is actually pretty good too. Now our cheetahs are right here. It's the same line of animal. And if you implement new motors, we can actually going down to almost like a human level. So that's all before applying any additional mechanism like spring return mechanism. You can actually, we have a paper of a para spring, for example. You can mitigate the peak torque to minimize the I²R. Without all those things, we can actually achieve the same level of animal. So if you include that, we could achieve efficiency of flying animal. So which means it could be better than old bad cars. So now you can imagine why I'm trying to build a robot, maybe 5, 10 years. I can ride and then go upstairs. Probably I don't need, hopefully I don't need to, but like some people might need something like that. They cannot move carefully, they need help to get in the car. You might even need a roads anymore. Car is great if you have roads. So we're claiming that if you have a really flat roads, we cannot beat cars. They're round. It's much better. But if you just generalize road, I think we can actually beat the wheeled systems in terms of efficiency. So if you summarize it, this is a peak torque for new motors. 170 Newton meter for that size is almost same as my ankle torque, peak torque. And high power, high power is not a good metric to think about in this kind of dynamics robot. If you really want to measure it, we can easily achieve a continuous 400 watt. And peak can go up to much higher, but those are not important metrics. We never even get to that power because it has a joint limitation. Torque is important. Impedance variability, I think we have no problem on that. And it can be high bandwidth. Efficiency, these are all estimated number. But that's where we actually win over muscle. Our actuator, if you design properly, you can achieve around 50% overall in the locomotion. This is what do you mean by efficiency? I'm talking about how much electric energy comes in, how much mechanical work come out, how much is burning through the ice core. Completely depends on how you're running. So let's finalize with some control algorithm. There's so much detail because it's a complex machine. But I'd like to introduce what kind of hypothesis, what kind of assumption was based on this algorithm. First, our idea is pretty simple. We think because it's kind of like bicycle, it's a long and skinny robot, we may be able to design sagittal plane locomotion first, and then combine with the frontal falling sideways, combine it to make it run 3D. That's one assumption. And second one is, this has come out from long pondering about what is our control policy? What are we trying to do? Of course, we try to run without falling, but before that, how do we know how much force I need to generate these steps? When I'm running, what am I really thinking? What am I prescribing? Feed forward coming on. Of course, feedback, something going on, we don't really know. But something we already know even before hitting the ground. And what we are trying to do, so I hypothesize, we have to follow physics that animal or robot, if you run it, if you integrate the normal force, vertical force over time, if you steady state integrate over a long time, the amount should be same as mg times delta t because your momentum should be conserved. Vertical moment should be conserved. So if I know my speed, if I know how long does it take to return my leg, I know exactly how long my leg is staying in the ground respect to the total time. I know duty factor of my leg. And I know how much impulse I need to get from that step. If I fix the swing time. So if I fix the swing time for other reason, and we don't know that's a good way, but if you fix the swing time, no matter what, walking or running, now I know each step, how much impulse I need to get. I don't know what profile is better, but I actually don't care too much. So how about anything that's physically possible, like sine curve, or we actually eventually optimize it. But that was one of the assumptions. And we built our finite state machine based on our intuition. Well, we need to protract, we need to have some swing leg retraction phase to match the speed, and then follow through. Those are basic assumptions of this galloping control. This is the equation I'm talking about. This doesn't satisfy, doesn't guarantee. It's just a necessary condition, not sufficient condition. So we need to add more. But this is what we get. This has been about a year now, waiting for to be implemented. So it change the gate and accelerate up to 5 meters per second. Changing gate was just a hand-tune the gate and going down the step, and it's pretty robust enough on a continuous rough terrain. So I want to briefly explain this process. We model an 11-degree freedom, Cheetah, and then we optimize to create a limit cycle. Limit cycle means I start this position and then come back to the same position. If you find that trajectory, you can just repeat it without guaranteeing your stability at 3 meters per second. And these are optimizing parameters. There are quite a number of parameters. I think it was 60 or something. And then once you get limit cycle, now we need to make it stable. So what we did, we convert all the things, the control parameter that is function of time, change into function of state, because time is bad, because if something drifts, it's not going to match. And we add impedance around our desired trajectory, because as I said, momentum balance doesn't guarantee your position, it guarantees velocity. Even though you get it right, we don't know even if our robot can do it. And there's some pattern stabilization algorithm, and then there's some speed control algorithm. So we make a 3 meters per second very, very stable. And what we do in getting faster, instead of optimizing for 4 meters per second, 5 meters per second, 6 meters per second, it's too much hassle. So we actually change only ground direction force profile following momentum balance. And then we try same optimization, the stabilization algorithm, only changing this, and you achieve 11.5 meters per second, no problem. So that's what we're showing here. So we only did optimization once to find limit cycle, and then have a stabilization mechanism, and then changing this momentum-based force profile prescription, and achieve pretty impressive result. If anybody's interested in cheetah-like gallop or horse-like gallop, there's some many type of different type of gallop. I love to talk about it, but it's just for those who are interested. And according to simulation, of course, simulation is not the perfect. At 33 miles per hour, our robot will consume only 2 kilowatts. I think that will be almost same level of, well, we don't know, it's actually almost same as an animal, but actually pretty impressive cost of transport for that speed. And then we're using exactly the same algorithm without knowing the height. It achieves 70 centimeter drop and 127 drop. This is point data. It doesn't really mean it covers all the height drop here. But it's pretty impressive. I think around less than 80 centimeter drop, there was no problem using same algorithm. And now we combine it. OK, so some simple capture point idea. Can we combine that algorithm into 3D? And you'll see the red arrow. That's the disturbance. And then you recover. That's pretty complex disturbance. It's not in the center of mass. It's actually tilt and yaw and roll. And they recover pretty well. And they're running at 3 meters per second, very, very stable. So we're waiting for that algorithm to implement here. We have a lot of discussion what kind of computer we're going to use. That surprisingly is a bottleneck for us. The reason why is our leg can shake 100 hertz, which means the loop time should be much, much shorter. And that caused a lot of trouble. We use FPGA significantly. Now FPGA is hard to redesign, recode again. So we are shuffling around the idea. That's why delay is going on. But hopefully we can get that pretty soon. Before going to the end, I want to show you something fun. I think a lot of people seen this one. But there's a reason why I'm showing this. This video bugs me for several years. Even though I'm not a control expert, this didn't make sense. With that slow feedback loop, maybe chicken is faster than human, but it's animals are the same. How can they perfectly reject the disturbance from the human, which is unexpected for chicken? Then they're close friends, but not that close. They don't know what exactly this guy is doing. Somehow, there's no delay even. There's like a reject from the beginning. And we know animals use their eyes and vestibules and then proprioception to control their balance, all that. How is it even possible? And I think this is actually known to biologists for a long time. There is actually additional vestibule organ in their pelvis. In robotic term, there's another IMU in their pelvis. I don't think human has it. I don't think my pelvis can measure orientation. Every bird has a separate IMU in their pelvis. And then people are speculating, I think one is mostly used for birds, flying, one is for walking. I don't know. I don't think people know exactly. But that might be very useful. If I have one IMU in my cheetah head, one in my IMU in my body, I might be able to stabilize my head. Now I can utilize my vision to actually augment my IMU sensing because IMU will drift. Inspiring, a lot of questions. So, there's many other projects, old project, a new project. I want to show you, we are also making a printable robot and actuator. So I'm focusing on actuator. Our postdoc developed this layered-based pneumatic actuator you can actually print. So we're actually making this pattern out of CNC milling machine and heat up and just punching. So you can actually make actuator in 1 second. So you design computationally where the actuator should be in layer 2 vinyl, I think, and then you can just punch. You can make an actuator like that. So we hope that we can make a layered process, get this multi-layer structure, fold it up, and then start walking and running. I wanted to show this. This is coming from this frustration for FPGA. God, I want to have something I can easily code. We designed this, undergrad, fantastic undergrad, designed this in 2 or 3 months. The cost is about $1,000, including treadmill. We bought $200 treadmill. It was there. So I designed this for education. Right now I'm teaching biomechanics, bio-inspired robot class, and then I give the half cheetah to every team. I have a 10 team. I didn't give you all this design because they're gonna pick a problem. They're gonna pick a throwing or kicking or walking, jumping, but they have all the materials to do this. And then these are $30 motor and then $50 processor, and they're multiple processors. So it started walking. I think one joint was not moving, and he didn't know that. Sent me the video, but it's strong enough. If I can find this cursor, and it's cheap. It's $1,000. Not that cheap, but it's way cheaper than our Cheetah, and very, very safe. You can just use a $500 power supply, and these motors can be 3 times or 4 times stronger if I change this magnets and I can do something. And the design principle is exactly the same. We don't use a force sensor because that's causing too much trouble. Non-collocated sensing, instability, I don't want to deal with that. We use exactly the same torque control with the own very bad encoder. It's doable. The sensors are very noisy. The signals are very noisy. Global mechanical dynamics is so slow. It's still good enough to do a class project. So they're going to do throwing, jumping, same impedance control. Now we can do in class. So to close the talk, we have a lot of biological data for their purpose. Biologists still interested in how biological systems work. And then we try to learn from it, but the obstacle is such a big problem. We need to cross the domain, and the technique has to go through this abstraction process and then make it happen and meeting these requirements. That's an important message. As we did with the biological, in the flying machines, we learned from biology, but we got inspired. We wouldn't probably even thinking about making plane if you haven't seen flying animals. They give us really new perspective, as I show in the gecko, give us new idea what stickiness, define new way of locomotion. I think the principle that the inspiration is actually the most valuable source we have in the nature. And I want to thank many, many people behind this video, work hard and stay all night, exploding batteries, and I want to thank, and then I'll open for questions. Thank you very much. So, any questions? Yes?
So, we're sitting here burning about 100 watts each. If we run probably another 100, 150 watts horizontally, running up a hill or upstairs, maybe we get to 500 watts, real work.
Possible, yes.
Yeah. Your Cheetah is running at 2 kilowatts or so, but the difference running upstairs should be about the same 200 or 300 watts. Have you done it?
If by our Cheetah,
If you tilt the treadmill, that 200 watts difference the real work should be about the same as for us. That's the real work, the mass times.
If you climb up, yes, you have a real work. So you have to add that real work onto this locomotive energy loss, yes. Yeah.
Have you tried it?
Well, treadmill tilting doesn't really work because your potential energy still stays same.
Yeah, that's true.
Yeah. Your kinetic energy is also the same.
No. What's your work?
Your potential energy is the same. No, if you draw a system by your body stay, kinetic is the same, potential is the same.
Yeah. Not in the Newtonian reference frame of the treadmill belts.
Well, if you have a different treadmill, yeah, if you have some certain treadmill, you can actually do work 4 times the distance. But if you have a treadmill that doesn't, well, if you ignore the inertia, if you have a perfect treadmill, you don't work, right? It depends on how you design a treadmill. Yeah.
Ooh, that's
Yeah. It depends on how you control the treadmill.
Running at
It's true.
constant speed, you're doing work. The treadmill is constant.
Yeah, it depends how you control the treadmill. Yes, true. Yeah. If you treadmill doing something, so you need to produce more force than you're walking on the ground, you'll probably consume more energy. Yes. But if you design massless tread, no motors, if you're like running like this, you probably don't need to do any additional work because your kinetic is the same, potential is the same, your impact force should be same as the running on the ground.
It's harder at the gym to do.
Let's talk more offline.
Yeah, sure.
Next question.
Yes.
Yeah. Ignoring for a moment the efficiency, do you run into thermal limits in the actuators?
So that's, we need to have a little better thermal modeling.
If so, have you considered fluid cooling?
You consider fluid, like the fluid cooling, yeah. We haven't thought about it. Because we've been focusing on like how fast we can run. So we actually thinking about phase changing material instead of circulating fuel because we only want to run a minute or so. I mean, you know, Cheetah probably don't run more than 1 minute either. We're not even that speed, but you know. So yeah, if you want to do high speed, long distance high speed, you want to do cooling. But for like a how can I say, long distance speed, like 4 meters per second, our motor can do continuously. So that it depends how you run, and you need to have a better thermal modeling. Yeah. Yes.
So you have no springs at all in your system.
In our system, there's no spring besides the plastic leg, which
So the energy efficiency is coming in because of the regen.
is actually not. Frankly speaking, is that not that big? It's only 10% or so. Energy efficiency comes from not burning unnecessary energy through gearbox.
Right. Or
And
just
then
swing.
having high mass smacking on the ground. So this is not nearly even close to be the best. You can actually add a spring, parallel spring. You can save another 50% energy in our paper theory. Haven't tried yet because that ruins our controllability. I need to do a lot of feet 4 times to compensate all that. But so if you think about all that, eventually it's going to beat the car in general terrain, not on like smooth circuit surface terrain. Yes.
Can you explain a little bit how you calculate cost of transport? Because I'm very surprised that with the higher speed, you get lower cost of transport, which is in the reverse. So in reality, inertial work done is speed squared.
Yeah.
So how come this
Power is increasing, the cost of transport is decreasing. Cost of transport normalized by the speed, so it can decrease if it is better running. For example,
Yeah, but how can that happen?
maybe not this one.
No.
So of course, in this range, if your speed goes up, cost of transport goes down because they like the speed dynamically better than this, including muscle physiology, all that.
Yeah.
So that can happen, but in typically animal, their preferred speed range is very narrow. And I think the smaller animal, this is more flatter. They don't care too much in smaller animal because gravity is not that much. Heavier animal care more. So probably our cheetah still want to go faster for truck. Again, I think it's because of the center mass fluctuation gets smaller. You do less negative work, positive work, and the speed is not expensive in our electric motor world. In most of the world, that's not true. I think that's why, yeah.
And here you were mentioning that in the galloping, why should you do galloping? So do you consider the spine deformation that helps a lot for the
I actually don't know yet, and I don't believe it's going to help efficiency. I believe it will help to get higher speed, I think.
Yeah, and speed, because you will increase your stride length size.
Yes.
Because by extending your body more, it's extending its body so much.
So the main reason we have a spine is actually to find out the truth of this 30-year-long speculation. Nobody really proved it. So actually, we designed the spine in a way that fairly we can compare, because we didn't add actuator. If you add actuator, consume more energy faster, is not very interesting. So we actually couple it. We can actually couple it, so we can compare it. But unfortunately, we had a delay, so we haven't showed it yet. I think actually galloping might be much more expensive than trot in general, because more fluctuation. Any other? Yes.
Quick question. Where can we buy these awesome new high torque density motors?
So the one that we're using is actually commercially available. It's Imotech motor. I wasn't very impressed by this torque, peak torque, because they advertise it as 20. And then we realized it's already saturating at 10. So that's what I'm saying. I called company, how can you do that? And they're like, well, we actually didn't test it. So let me tell you the truth. So most company, they measure the motor constant, and then they usually give you the voltage. And then if that voltage, how much torque you can get, just extrapolate, and then just give that number out. Many companies does that. So they don't know when the steel saturate. That's why new motor, we actually use a special metal that increases the saturation density. That's why I get higher max. And then also gap radius got larger, even squish more. And we are actually developing 6-phase motor right now. I'm a little bit scared because the electric complexity, again, electric complexity is not an important cost. Eventually, I still love to develop homopolar rotary motor. I think it's topologically impossible, but if it's possible, I love to do that. So make it cheaper. So yeah, the answer is you can buy something not as good. This one, I think, is way too expensive at this point. Yeah.
We looked at central pattern generators.
Yes. Yes.
How are they?
Like central pattern generator of animal, or?
Yeah, well, for use in your robot.
In our simulation.
Yeah.
Central pattern generator is a hypothesis. I don't know what I have to compare with. We have a pattern generator. I'm not really sure if we should call central pattern generator, because many people use different way of the definition. Our central computer is prescribing pattern. So, you know what I'm saying? So we compare with the animal step, it was similarity, but especially gallop. Every gallop trots are the same. Gallop is completely depends on speed. Even small dog has a gradient of a pattern. It depends on speed. So I'm not really sure how to compare with the animal. Yeah. Yes.
So in the motor, you said that the shorter motor was better than the longer, and
the more precisely larger radius matters.
Larger radius motor. But there was an assumption that the wall thickness was always kept the same. So what was the thickness you said that what was the reason for that assumption?
So that was just to minimize the complexity of the model. If I open that up, the dimension analysis, scaling analysis would be more complex. So you can optimize it, possibly, but I'm not really sure you can include all that. So I like to have a simpler design principle so you can actually implement it. If you do optimization, if you do something wrong, it's hard, like an N-turn is when it goes smaller, larger. You have to include a lot of stuff. Saturation doesn't happen at once. Saturation happens locally and then spread out, sometimes move around. It's very complex, actually. So before going into that detailed optimization, I want to have a simple rule. As a designer, I need to have a simple rule so I can design at the same time multiple things. So yeah, that thickness usually is defined by determined by the magnetic strength. Like if you have a longer magnet, you can get higher strength, and then actually higher demagnetic torque. But that also saturates at some point. If you thinner magnet is thinner than better. But if you reach at some point, it's almost same. So you don't need to increase that much anymore. And that has to do with the stator thickness. Stereo techniques is a little more hard to explain. I don't have knowledge enough knowledge to explain that part. Any other questions about anything? Yes.
In the riding, I think there is another stage of canter in between the trot and the gallop. You're kind of skipping that. You skip that in your cheetah robot.
In our case, I think so. Yeah. I have actually video of exactly canter, but it was cheating because one of the string was holding the cheetah every time it hit the ground, and students didn't know that, and then pelvis severed in half, and then they were like, "Oh, we're running too hard," and I was like, "Look at the video." What your cheetah is doing is tugging the wire all the time, and that's what it's like. So you can run canter, I think, but that's actually the whole point of research. I want to know the effect of gait and what is energy efficiency and stability. I'm not sure how much I can comment on that. Yeah. But I would love to try it. Yeah.
Okay, great. We've got a reception to go to, so let's thank our speaker.